Today, I will be talking about tight quantum time-space trade-offs for function inversion. This is a joint work with Qipeng, Chung, Siyao, and Luowen Qian. Function inversion is the following problem. You are given a function f and some image y. The goal is to find any pre-image of y. Classically, the problem requires a brute force search, which takes time linear in n, and this is known to be tight. Quantumly, Grover search can be used to achieve a quadratic speedup. This is also known to be tight. In this work, we are interested in the following problem. What if we can prepare an arbitrary S-based advice that's only about the function f, and then use this advice to do function inversion with fewer queries? This is a real threat to practical cryptography. In practice, breaking a crypto system is usually do function inversion over some publicly known function f. An attacker would simply do very heavy computation on the crypto system to get some advice, and later it can use this piece of advice to break the system much faster. It also helps us understand the non-uniform circuit complexity of the function inversion problem. And finally, the problem also has connections to well-studied problem in data structures and also communication complexity. We know in the classical setting, Hellman trade-off achieves the time-space trade-off st times t less than n squared for functions. In other words, if an S-bit advice is allowed, the number of classical query to do function inversion is roughly n squared over s squared. The same algorithm achieves the trade-off st less than n for permutations. For lower bound, Yao and Uru proved the lower bound st greater than n. This is tight for permutation. However, we see a barrier between the lower bound and the upper bound for functions. Later, Corrigan, Gibbs, and Kogan showed that any improvement would result in a new lower bound for circuit complexity. In this work, we consider quantum query complexity with the following two scenarios, namely classical advice or quantum advice. In other words, we consider an algorithm with either classical or quantum advice and can make quantum superposition query to a function. The only known quantum algorithm with advice is to use the classical Hellman's trade-off or use Grover search. Given S and T, one can choose either Hellman's or Grover's, depends on the parameter. We notice that for Hellman's trade-off, it is only a classical algorithm using classical advice, but Grover algorithm does not use any advice. So in this algorithm, advice does not help speed up the quantum part. So it's natural to ask the following question. Could advice help speed up Grover search? This problem was first proposed by Naibi, Arison, Belows, and Traverson in 2015. They show that for classical advice and random permutation, they achieved the lower bound st squared greater than n. Later in 2019, Han, Sagawa, Yamakawa shows that the same lower bound holds for classical advice plus permutation or quantum advice with classical advice with function or quantum advice with permutation. More recently, Chung, Liao, Qian extend this result to the case of quantum advice with permutation and some functions. It only applies to functions whose domain and range are of the same size. However, they do not rule out the possibility that a piece of advice could speed up function inversion, because if you solve the equation, it gives you t is roughly square root of n by s. In this work, we answer the question by showing by improving the lower bound to st plus t squared greater than n for quantum advice and functions. Now we draw the trade-offs in the picture. The x-axis is for S and the y-axis is for t. Namely, if a point has 0.5 in x-axis, it means S equals to square root of n. Now, this is the line for Hellman's algorithm. The classical lower bound achieves this line. As mentioned before, we know that there are barriers in the area between these two lines. For Grover's algorithm, it gives this upper bound, which is the red line here. And all the previous result that gives the quantum lower bound, which is this blue line. And this orange line is our new bound. For S is at most square root of n, which is the left part of the line. This is tied to Grover's search. In other words, if S is small, even quantum advice does not help Grover's search. And for S is large, the bound is the same as classical lower bound, which is the best possible lower bound, considering the barrier mentioned before. In this work, we also provide a generic framework for proving quantum time-space trade-offs and use it to solving the following problem. The first one is Yale's box. Let f be a function with binary output. Also, again, we assume we're additionally given s bits or s qubits advice about the function f. The question is, can we learn f of x by querying f prime t times? Well, f prime had the same functionality as f, except it outputs nothing on the point x. The problem in the classical setting are recently studied in the context of circuit complexity. For s equals to 0, the best we can do is simply random guess, as there is no information about fx. And here is the example for s equals to 1. The advice alpha is simply a single bit, which is the parity of the function f. In the online phase, let beta to be the parity of the function on all inputs other than x. And fx is simply equals to alpha XOR beta. So to compute beta, it takes n-1 queries. So overall, it gives us t equals to n-1 queries. And more generally, by extending the algorithm for s equals to 1, we can get a classical algorithm that works for any s and achieves t is roughly n over s. In this work, we resolved two open questions from Nayebi et al. For Yale's box. For classical advice, we show a lower bound which is st greater than n. This is improved from st squared greater than n by Han et al. This is tied to the classical algorithm, which shows that the power of quantum query does not help Yale's box with classical advice. For quantum advice, we show a first non-trivial lower bound, which is s to the 5th times t greater than n. In 2018, Karate, Dodis, Gore, and Steinberg shows the statement that sorting generically prevents preprocessing attack in the classical setting. Well, sorting is a common mechanism used in practice for defeating auxiliary input or advice in our work. We extend the statement to quantum preprocessing attack. We first show a generic lower bound for any cryptography with salt in the quantum random oracle model. And we also answer the question raised by Han et al. By showing a first generic lower bound for solid collision resistant hash function. Now, let's look at the proof overview. Our proof consists of the following two steps. We reduce the lower bound against advice to a variant of multi-instance game lower bound. which is similar to direct product problem. We do this by construct algorithm for multi-instance game without advice from algorithm with advice. For classical advice, we use a simple reduction. For quantum advice and quantum advice with decision game, we use some different tricks. For this presentation, I will mainly focus on classical advice. The next step is to give a lower bound for multi-instance games, which then will become a lower bound for the time-space trade-offs, or the algorithm with advice. Now, let's look at the first reduction, which we construct algorithm for multi-instance games without advice from algorithm with advice. We first introduce direct product problem. We will focus on the formulation of everything 05. This is the definition of direct product of solving S instances of function inversion. Basically, the algorithm is given S independent image y1 to ys, and the goal is to find all pre-images for every yi. And let A be a T-query quantum algorithm with advice alpha and success probability delta. We want to construct an algorithm B, which solves the direct product problem with classical advice alpha and success probability roughly delta to the S, where S is the number of instances. And this is what B does. Given all the inputs, B simply gave the advice alpha and y1, which is the first challenge to A, and outputs the pre-image with probability delta. And similarly, alpha and y2 give to another instance of A and output x2, and so on. So we notice that each xi is outputted correctly with probability delta. So overall, the success probability is roughly delta to the S. Now we already have a ST-query direct product solver with probability roughly delta to the S. And in this step, we try to remove this advice. So we simply guess the advice by flip a bunch of coin. And we know that because advice only has length S, so with probability 1/2 to the S, the random coin will equals to exactly alpha. So therefore, by toss the random coin, we have a ST-query direct product solver with success probability delta over 2 to the S. Now let's recap our reduction. What we have shown now here is if we have a T-query algorithm for function inversion with probability delta and advice size S, then we can have a ST-query algorithm for the direct product problem without using any advice and with probability roughly delta over 2 to the S. Next, we hope to prove this ST-query algorithm cannot win the cannot win the direct product game with probability better than this, ST plus T squared over N to the S, which will give a upper bound for delta, and the delta is the desired bound we want. However, I'm going to show that it is indeed impossible. We're going to show a quantum algorithm based on Grover search, which solved the direct product problem much faster. The green box is the Grover's algorithm. And in the first round, it takes y1 and ys, and the goal is to find any pre-image of this y1 or ys. And we know that Grover's success probability is roughly p times t squared, while p is the density of all valid inputs. And we know that because there are totally y images, so the probability or the density is roughly S over n. And we totally make t Grover iterations, so the total probability is st squared over n. Therefore, we have already find one of the image, one pre-image of any images. So for the second step, we try to find a pre-image for any yj whose pre-image has not been found before. And with a similar argument, we find that the probability is roughly s minus 1 times t squared over n, because we now have one less image. And more generally, for the case step, the probability of finding a pre-image is roughly s minus k times t squared over n. So overall, the probability is the product of everything, which is roughly s factorial times t squared over n to the s. And this is roughly st squared over n to the s. And we find that this is much larger than st times t squared over n to the s. Therefore, we know that the best lower bound using direct product is the same as all the previous quantum lower bound. So to overcome the barrier, we introduce sequential direct product, which we call multi-instance game. Instead of getting all challenges at once, the algorithm is now getting them one by one. And it needs to answer the previous challenge before getting the next one. And also it has at most t queries to produce the answer for the current one and sends it back to the verifier. In other words, instead of getting y1 to ys together, it gets y1 at the beginning, and B can make at most t queries to F and produce x1 before getting y2. And then it gets y2, B make another t queries and outputting x2. And finally, it outputs xs. Note that the previous Grover parallel search is no longer possible, as to do the algorithm, one needs to know all y at the beginning, which is impossible in the game. And therefore, we can use exactly the same reduction before, and we obtain an algorithm for the multi-instance game with success probability delta over 2 to the s. And next, we want to give an upper bound to the success probability of the multi-instance game. Let's say it is gamma to the s. And look at these two equations, we know that delta is at most 2 gamma. Therefore, gamma is an upper bound on delta. And delta is the probability we want to bound. And in the second step, we show how to prove the lower bound for the multi-instance game, or in other words, bound gamma. So let B be any quantum algorithm, then B inverts all the images. The probability is the product of this probability. Well, the ith probability is B inverts the ith image, condition on it inverts all the previous images. And our goal is to bound each probability separately. Before looking at how to do it quantumly, we show the proof for classical algorithm. Let f be a random function. We use the lazy sampling methodology to do the proof. The lazy sampling methodology says that instead of sampling f at the very beginning, we can sample f of x whenever x is queried. Therefore, f can be sampled on the fly. Now, let us look at the proof. In the ith stage, we know that all the previous I-1 images has been answered. And also we know that B has made at most IT queries. By the lazy sampling statement, only IT position of F have been sampled, and other entries of the function are still completely random. Therefore, when the next challenge yi is sampled, there are two cases. Case 1 is it has been queried by B. Case 2, it hasn't. In case 1, yi has been queried by B. Since B only knows it entry of the random function, so and also the challenge yi is sampled uniformly at random, so we know that case 1 happens with probability roughly it over n. In case 2, it has not been queried by B, because we know that B has no information about yi, so by making t queries, the probability that B hits yi is roughly t over n. Therefore, the total probability is roughly it over n for the ith round. So we know that the overall probability is roughly this, because each for the ith probability is roughly it over n. So therefore, overall is st over n to the s. And therefore, gamma is roughly st over n. And gamma is an upper bound of delta. So we know that delta is at most st over n. Therefore, we have st should be at least n. And so we reproduce the classical proof, but using a different method. To prove the bound for quantum algorithm, we derive the following lemma. Consider the game. The algorithm A can make Q0 query to the random function, and it then gets a challenge Y. It can make another Q query to the random function, and finally output a pre-image. The lemma says A inverts Y with probability at most Q0 plus Q squared divided by n. And the lemma says the quantum query made before getting Y does not help it quadratically. It only helps it linearly. To prove the lemma, we build new techniques from a quantum version of lazy sampling, namely compressed oracle by Mark Zendry. Now let's try to prove the lemma informally. After A makes Q0 queries, a uniform Y is sampled. And there are two cases. Case 1, Y hits Q0 queries. Well, this is a quantum query, but it only happens on Q0 over n fractions of the state. This is by compressed oracle technique. Case 2, Y does not. And if case 2 happens, we know that the lower bound is almost the same as Grover's lower bound, because in case 2, there's no information about it, the challenge Y. So therefore, we have the probability that A inverts everything is Q0 over n, which is the probability that case 1 happens, plus Q squared over n, which is the probability that case 2 happens, and also it inverts the pre-image correctly. Therefore, by the previous lemma, we find that this probability is roughly it plus t squared over n. So overall, the product is st plus t squared over n to the s. And therefore, gamma is roughly st plus t squared over n. So we show that gamma is at most st plus t squared over n, and thus delta is also upper bounded by the same amount. And therefore, we have st plus t squared should be at least n, and this is the desired lower bound for classical device. I would like to have more discussion on direct product versus multi-instance game. Direct product usually achieve tight bound in the classical setting. There's almost no difference between direct product or multi-instance game in the classical world. But we have shown in the previous proof that there's a separation of direct product and multi-instance game in the quantum setting. Therefore, we believe the formulation of multi-instance game is more quantum friendly, and we propose it as a general framework for achieving tight quantum time-space trade-offs. Therefore, we conclude the proof. And that's everything I want to talk about today. Before ending the talk, I want to propose the following open question. The first one is a tight time-space trade-off for permutation, as our work only focuses on functions. The second one is to get any non-trivial quantum speed up for function inversion in this regime, which is the regime here, and there's a classical barrier in this regime. And finally, we believe our time-space trade-off for decision game are not tight. It would be very interesting to tighten the result. And that concludes my talk. Thanks.